solution of differential equations. Okay, the differential equation is representing a system is given by d square y upon dt square plus omega square y equal to 0. Multiplying by 2 dy by dt we get multiplying by 2 dy by dt we get 2 dy by dt into d square y upon dt square plus omega square 2y dy by dt equal to 0. Okay, equal to 0. This is the equation number second and this is the equation number first. Okay, integrating we have integrating we have dy upon dt the whole square equal to minus omega square y square plus c, minus omega square y square plus c. Okay, integrating of both sides, then the d square or dy upon dt, dy upon dt, dy upon dt whole square equal to minus omega square y square plus c, y square plus c, because dy by dt, integrating dy by dt square is dy by dt plus c. Okay, so this is the constant what is dy by dt, then dy by dt into dy by dt, dy dt whole square into 2 equal to omega square 2i dy by dt, integrating dy by dt also converted in y, then y into y square omega square 2 equal to proportionally constant c, but this sign is transposing on LHS side, transposing on RHS side, then this sign is also converted in negative signs. So dy by dt whole square equal to minus omega square y square plus c. Okay, then where c is a constant of integrating, and when the displacement is maximum, when the displacement is maximum, then y equal to a, where a is the amplitude of the oscillating particle, where a is the amplitude of the oscillating particle, okay, oscillating particle, comma, dy by dt equal to 0, is that the particle is momentarily at rest in the extreme position and begin its journey in the backward direction, then substituting y equal to a and dy by dt equal to 0 in the equation number second. Okay, the particle is momentarily, where is the amplitude of the oscillating particle, and dy by dt equal to 0 because dy by dt is speed and the extreme position the speed is 0. Then dy by dt equal to 0 because velocity is 0. The particle is momentarily at rest in the extreme position and begins its journey in the backward direction. Then substituting y equal to a and dy by dt equal to 0 in equation number second, we have we have capital C equal to A square omega square. Capital C equal to A square omega square, because dy by dt equal to 0. dy by dt equal to 0. Sorry, this is the equation number second. dy by dt equal to 0. dy by dt equal to 0 and y equal to A, then the A square omega square plus C, if minus A square omega square is transposing on left side, then C equal to A square omega square. Substituting this value of C in equation number 2, we get substituting this value of C in equation number second, we get dy by dt whole square equal to omega square A square minus y square. Okay, dy by dt equal to dy by dt equal to omega under root of A square minus y square. A square minus y square. This equation gives the velocity of the particle executing simple harmonic motion at time t when the displacement is y. This is the velocity of the particle. This equation gives the velocity. This equation gives the velocity of the particle executing simple harmonic motion at time t when the displacement is y. Then dy upon under root of A square minus y square equal to omega dt integrating we get sine inverse y upon A equal to omega t plus phi. Then omega t plus phi. Then omega t plus phi. Then this is 1 minute. This is sine inverse y upon A equal to omega t plus phi, and this is y equal to A sine omega t plus phi. Okay, this is the equation number 4. Where phi is another constant of integration. The term omega t plus phi represents the total phase of the particle at time t, and phi is known as the initial phase of the phase constant. Okay, the term omega t plus phi represent omega t plus phi represent the total phase of the particle at time t, and phi is known as the initial phase or phase constant Okay, if the time is recorded from the instant when y equal to 0 and increasing then phi 0. Okay, and if the time is recorded from the instant when y equal to 0 and increasing then phi equal to 0. Okay, thank you. And next is other solution of simple harmonic motions equations. Okay, other solution of simple harmonic motion as system. Okay, the equation y equal to a sin omega t plus phi, y equal to a sin omega t plus phi is just one solution of differential equation d square y upon dt square plus omega square y equal to 0, omega square y equal to 0. Okay, then an equally valid solution of this equation is y equal to a cos omega t plus phi, a cos omega t plus phi. Expanding y equal to a sin omega t plus phi, we have y equal to a cos phi sin omega t plus a sin phi cos omega t. This is sin a plus b, sin a plus b equal to cos sin a cos b plus cos a sin b. Okay, sin a cos b plus cos a sin b. Okay, then y equal to a cos phi sin omega t plus a sin phi cos omega t equal to capital A sin omega t plus capital B cos omega t. This is the equation number 6 and this is the equation number 5. This is the equation number 5 and this is the equation number 6, which is another valid solution. Y equal to then a equal to a cos phi and b equal to a sin phi. Okay, then a equal to under root of a square plus b square, because a square plus b square, the value of a square is a square cos square phi plus the value of b square is small a square sin square phi. Then a square plus b square equal to a square common, then in bracket cos square phi plus sin square phi. The value of sin square theta plus cos square theta equal to 1. Then a square equal to capital A square plus capital B square. Then a equal to under root of a square plus b square. Okay, this is the value of small a, and b is divided by a. b is divided by a, then b by a equal to a sin phi upon cos phi. A is cancelled out by 8, sin theta upon cos theta equal to tan theta, then but the place of theta is phi, then tan phi equal to b by a and phi equal to tan inverse b by a according to trigonometry rule. Okay, according to trigonometry rule. Okay, then the variation, then phi equal to tan inverse b by a, Okay, A equal to under root of a square plus b square and phi equal to tan inverse b by a. The variation general solution of differential equation in since cosine form are first in sine cosine form are y equal to a sine omega t plus phi and y equal to a cos omega t plus phi and y equal to a sine omega t plus b cos omega t. Okay, and second position exponential form exponential form. We can put differential equation 1 in the operator form by substituting d upon dt equal to capital D or d square upon dt square equal to d square, and we get d square y plus omega square y equal to 0, then capital D square equal to minus omega square, then d equal to plus minus I omega. The value of minus 1 is I omega. Hence the general solution of equation first becomes y equal to capital A power I omega t plus capital B E I omega t. Okay, in order that the solution may get a real value of y, a and b must be complex conjugates of each other. Okay, then a equal to a plus ib and b equal to a minus ib. Okay, then a second form of the general solution of equation first is y equal to a e the power omega t plus phi and second this is the second form of general solution of equation first is y equal to a e to the power I omega t plus phi. It has two constant a and phi. It has two constant a and phi and satisfy differential equation first. Thus the solution of differential equation in exponential form are y equal to a e to the power I omega t plus b e to the power minus I omega t. Okay, and sorry, this is minus I omega t and a y equal to a e to the power I omega t plus phi. Okay, all these alternative ways of writing the solution of our differential equation first have their own advantages for a particular problem. We select the form most convenience for the purpose. We shall use the solution y equal to a sine omega t plus phi in general. Okay, in general omega t plus phi in general. Okay, then simple harmonic motions is sinusoidal or cosinusoidal, or simple harmonic motion can be represented by the Simple harmonic motion is sinusoidal or cosinusoidal, or simple harmonic motion can be represented by the relation y equal to a sine omega t plus phi and y equal to a cos omega t plus phi. Okay, where y is the displacement, at a time t small, a is the amplitude, and omega is the angular velocity. And frequency, angular frequency, and phi is the phase constant. Okay, phase constant. Phi is the phase constant. And the equation number first, we have dy upon dt equal to a omega cos omega t plus phi, and d square y upon dt square equal to minus a omega square sin omega t plus phi, and equal to minus omega square y. Similarly, from equation number second, this is the equation number first, this is the equation number second, and this is the equation number third. Similarly, from equation number second, we have dy upon dt equal to minus a omega sin omega t plus phi, and d square y upon dt square equal to minus a omega square sin omega t plus phi, okay, minus a sin omega t plus phi, and d square upon dt square equal to minus a square omega square cos square phi, cos square phi a square omega square cos omega t plus phi. This is minus omega square y. Then according to relation fourth, this is the relation number 4. According to relation third and according to relation fourth, the acceleration d square y upon dt square is proportional to displacement y, and is directed towards the mean position, which proves that the motion represented by the equation number first. Second is simple harmonic motion. This is why a simple harmonic motion is called sinusoidal or co-sinusoidal. This is why a simple harmonic is called sinusoidal or co-sinusoidal. Okay, thank you.